Hello everyone, so you'll remember that we're interested in using information about the derivative to tell us something about the function. So in this video, we'll talk about the mean value theorem, which is an important tool for doing that. We'll get to the precise statement a little bit later, but there are two kind of intuitive ways to think about it. The first way to think about it is if we have the graph of a function on an interval, then at some point the slope of the tangent line equals the slope of the secant line joining the endpoints. So that is one way, and we'll see some pictures. And another way is if we have some kind of physical process, then at some point the instantaneous rate of change is equal to the average rate of change. Okay, so let's get to work towards the mean value theorem. And before we do that, we need to first talk about Rolle's theorem, which is a kind of baby version of the mean value theorem. So let's suppose we have a function which satisfies three conditions. So the first condition is that it's continuous on our closed-bounded interval AB. The second condition is that it's differentiable on the open interval, so differentiable at every point of the open interval. And the third condition is quite restricted. It says that at the endpoints, the function takes the same values. So f of a is equal to f of b. Okay, then the output of the theorem is that at some point c between a and b, the derivative has to be equal to 0. Or in other words, the slope has to be equal to 0. Okay, so whenever we have a function satisfying these three conditions, Rolle's theorem says that there is a number c where the derivative equals 0. And okay, why should this be true? So, I could, I could be a pure mathematician for a little bit and write down a very careful proof, but I think the idea is illuminated in the following picture. So here are some kind of examples of what could happen. So in each case, we have a function which satisfies these three conditions. It's on the interval AB. So it's continuous, it's differentiable, and f of a equals f of b. So the y value at the endpoints is always the same. And okay, kind of intuitively, what could happen? Okay, my function could be kind of boring, it could be constant. Okay, but then anywhere between I'm going to have derivative 0. Or it could go up a bit, and then, okay, I'm supposed to land it back at b, right? So if I start at a, I have to have f of a equals f of b. So what goes up must come down. So I have this kind of picture. Okay, but then in the middle, the slope is 0. Okay, and then the same story with the last one, but reversed. So if I start at a and I go down, well, if I want f of a equals f of b, I have to come back up. So it has to look kind of like a smiley face. And then let's see the slope is 0. So if f is constant, if it goes up and then down, or if it goes down and then up, whatever happens, if we have these three conditions, then somewhere in the middle, the slope must be equal to 0. Okay, and the reason this is not a proof, this is just the intuition, is because you could have, combinations of all kinds of things, right? The function could go up and then it could come down and then it could go up and then it could come down some more. It could be like sine or cosine or do all kinds of crazy things. But this is kind of the idea, and it works for any function with these three conditions. Okay, so mostly this is useful as a building block to get towards the mean value theorem. So, but let me first do an example using this. So let's suppose we have the following. So let's suppose we have f of x equals x cubed minus 15x plus 1. And we want to show that the equation f of x equals 0 has at most one root or at most one solution in the interval minus 2 to 2. Okay, and the strategy is going to be, so we're going to assume that there is more than one root. That is going to give us two roots, and then root means the function equals 0. Then we're going to use Rolle's theorem. Okay, so let's set that up. So if we want to use Rolle's theorem, remember we're supposed to know something about continuous and differentiable. So our function is very nicely continuous and it's very nicely differentiable, so we don't have any worries on that regard. Okay, and then as we said, okay, we're trying to show that there is at most one root. Let's suppose there are two and show that we get a contradiction. So this is an example of a proof by contradiction in mathematics. So we assume that we assume what we don't want is true, right? We assume that what we want is false. And then we're going to see we get something crazy, and then we can say, oh, well, this supposition must have been false, right? I must have been wrong in assuming this. Okay, so let's do that. Suppose there are two roots, c1 less than c2 and minus 2, 2, right? If we're saying there are two, I can assume that one of them is smaller. So I can assume c1 is less than c2. Okay, and then being a root just means the value of my function is 0. So in particular, f of c1 equals f of c2 equals 0. Okay, but now we have what we want, right? We have two function values and they're equal, and we can use this as our interval. We can use the interval from c1 to c2 and use Rolle's theorem because we have all three assumptions on that interval, right? We have, the function is continuous, the function is differentiable, and the values at the endpoint of c1, c2 are the same. So we can apply Rolle's theorem on c1 to c2. It gives us c somewhere in the middle. Okay, we don't know where, but it doesn't matter. It just gives us a number c so that f prime of c equals 0. Or if it doesn't tell us exactly what c is, it just tells us there exists a number c. Okay, so what's so crazy about that? Well, if we go back to our original function, we can actually calculate f prime of x and see what's going on. Okay, so separately to this, let's calculate f prime of x. Okay, we differentiate x cubed, we get 3x squared. Differentiate the minus 15x, we get minus 15. The 1 goes to 0. So we get 3x squared minus 15. We factorize out the 3. We get 3 times x squared minus 5. Okay, the zeros will be plus or minus the square root of 5. And neither of those are in the interval minus 2 to 2, right? The square root of 5 is bigger than 2, so it's not inside here. So actually, the derivative is not equal to 0 anywhere inside the interval in which we're working, right? We're actually looking for a solution in C1, C2, but that's within minus 2, 2. Okay, so we have two things to compare, right? We said just based on actual calculation and checking our function, we worked out the derivative. The derivative is not 0 anywhere inside minus 2, 2. But separately, using Rolle's theorem, we said that if there are two roots to our equation, then there must be a value of c where the derivative equals 0. Okay, so this assumption that there are two roots must have been false, so there can be at most one root. Okay, so this contradiction gives us what we want. Okay, but as you see, Rolle's theorem is kind of special because we need this fact that the value at the endpoints is different. So how do we change things? What do we do if the endpoint values are different? So this brings us to the mean value theorem, which is a very important, very useful theorem in calculus. So this is one of the gold theorems that you should remember when you leave the course, and could be fair game for us to ask you. So let's suppose that f satisfies both the following conditions. So basically, we take the conditions from Rolle's theorem and we drop the third one, which is the nasty restrictive one. So it satisfies both that f is continuous and that f is differentiable. Okay, then there is c in AB. So just like before, there is c so that something happens. But it's not so that f prime of c equals 0. Instead, it's so that f prime of c equals f of b minus f of a over b minus a. Okay, so we assumed a little less to begin with, or we assumed quite a lot less, but the conclusion was a little bit more messy, right? So we didn't pay as much, but okay, we had to pay the price in the end that we got a slightly different conclusion. Okay, so let's try to untangle what this means. So what is the f prime c and what is f of b minus f of a over b minus a, and how are they related? So before we do that, let me just remark that if you multiply both sides here by b minus a, you get f of b minus f of a equals b minus a f prime of c. So this is another useful way of writing it. And let me remark that it doesn't tell us what c is in AB. It doesn't tell us where is the value of c or how many values of c there are. So this theorem is going to be mostly useful if we know something about f prime of c for every c. So we'll see that in the applications on the examples that we do. Okay, so let's entangle. So geometrically, what does this mean? So suppose we have a function y equals f of x. We'll see a picture in a second. On an interval AB, then f of b minus f of a over b minus a is the slope of the secant line that joins the two endpoints. Whereas f prime of c is the slope of the tangent line at c. So this equation is saying that at some point c, the slope of the tangent line equals the slope of the secant line joining the endpoints. Okay, there's a picture on the next slide. And physically, what does this mean? Okay, the equation on the left, if we have some physical process, let's say, represented by f of x, like say f of x is distance or something like that, so that f prime will be speed. So f prime of c is the instantaneous rate of change, and f of b minus f of a over b minus a is the change in the output divided by change in the input. This is the average rate of change. So it's saying that at some point in time, the instantaneous rate of change equals the average rate of change. And just to maybe make this as concrete as possible, suppose I'm driving in my car and f of x represents the distance that I've traveled. So the derivative would represent the speed. Okay, what would these quantities be? Then f prime of c would be my instantaneous speed at some point. So the instantaneous rate of change of my distance. So f prime of c would be my speed at a point in time. And the right-hand side will be my average speed over a journey. So this is saying at some point my speed is equal to my average speed. And just to be kind of more concrete, suppose I start driving, and at some point I'm driving 30 miles per hour for a while, and then I get on the freeway and I start driving 60 miles per hour. Okay, so my average speed is going to be somewhere in the middle, right? At some point I'm driving 30 miles per hour, at some point I'm driving 60. Let's say my average speed is 45, so my right-hand side will be 45. All this is saying is that at some point in time, my instantaneous speed was also 45. And that makes sense, right? If I'm going to go from 30 to 60, at some point in time, I have to go through all the numbers in the middle. In particular, I have to go through the average 45. Okay, so there's nothing too strange about it, but it is a very, very useful fact. Okay, and here is the picture I promised you that talks about the geometric idea, right? So here I drew two different functions, so I'm illustrating the same thing twice, so let's focus on one to begin with. So we have this function which is in black, y equals f of x. And okay, the values of the endpoints could be whatever, it doesn't matter, they don't have to be the same now. And let's suppose this point is A and this point is B, and I draw in red the secant line. So the secant line, remember, is just a line that joins the two endpoints. So here is the secant line, and its slope has this kind of slope. Well, at these 2 points C that I highlighted, the slope of the curve, or the slope of the tangent line, or the slope of the curve, is equal to the slope of the secant line. Okay, mean value theorem said this happened at most once. This happened at least once. In this case, it happens twice, right? So we have 2 points where the slope at these points is equal to the slope of the secant line. Okay, and here on the right is another function, just for a variety. It's a different function. It goes down a bit like this. So this curve, like curve, is my other function. And okay, in red again, I drew the secant line joining the two endpoints. Okay, and here is exactly one value of C where the slope of the curve is equal to the slope of the secant line. Okay, but the beauty of the theorem is, I could draw 10 million pictures and I still wouldn't cover every case. There are always more functions you can draw. Whatever the function is, as long as it satisfies f is continuous and f is differentiable, then you get a C so that f prime of C equals f of b minus f of a over b minus a. Okay, so let's go on to see some applications and examples. So as we said, it doesn't tell us about the value of C. So it's mostly useful when we know something about f prime of x for every x, because then even though we don't know what C is, we can still say something about f prime of C. Right, if I said, suppose I said that f prime of x equals 0 for every x, then okay, you apply the mean value theorem, you get f prime of C. I would still know that f prime of C equals 0, right, just because all the derivative is 0. Okay, so here's a kind of first application. Suppose the derivative is 0 for all x, then f is constant on AB. Okay, so in other words, I can find a constant n. Doesn't have to be a whole number. I just wanted to use n to get away from using C all the time. So we can find a constant n so that f of x equals n for all x in AB. Okay, so bottom line, if the derivative is 0 everywhere, then the function is constant. Okay, and as for why this is true, if I go back to the statement of mean value theorem, let me use in particular this equation. If the derivative is 0 everywhere, in particular f prime of c equals 0, this would tell me that f of b equals f of a, right? F of b minus f of a equals 0. But I don't just want to know the value at the endpoints is different. I want to know that all the values of the endpoints are the same. I want to know that all the values are the same. Well, I could apply this on any interval that I like. In particular, I could apply this on an interval from a to some point in the middle, and I will get the value in the middle is equal to f of a. Okay, so the idea is the same. And then, okay, suppose we know, just an application of this, suppose we have two functions that they have the same derivative for every x in AB, then they differ by at most a constant. Okay, so I can find a constant so that f is g plus my constant. So this is going to be useful later when we look at integration and finding antiderivatives, which means reversing derivatives. So this is going to say, there is only one function with a given derivative up to a constant. If I have a derivative and I want to find the original function, I can do that provided I am willing to add on a constant for the different ones. Okay, so here are some more examples that are not really theorems, but just fun examples that are things similar to what you might be asked to do. So let's suppose we have a function which is continuous on 1, 4 and differentiable on the open interval 1, 4. And let's suppose we're given that f of 1 equals 10 and the derivative is always bigger than or equal to 2. Then how small can f of 4 possibly be? Okay, so we're not told anything about f of 4. We're just told the value at the left endpoint is 10 and the slope is at least 2. Okay, so let's see how that should go. Well, we can use the mean value theorem, right? So whenever you see this kind of language, continuous on a closed interval, differentiable on an open interval, that's a giveaway that you should think about using mean value theorem or Rolle's theorem. So we have those conditions, we should use the mean value theorem. Let's just naively plug in and do that. It tells us that there is C between the two endpoints, so that f of 4 minus f of 1 equals f prime of C times 4 minus 1, right? If you just copy the statement of the mean value theorem, this is what we get. And now we're interested in f of 4. So let's solve this equation for f of 4. Okay, I can write f of 4 equals f of 1 plus 3 f prime of c. Okay, so we just rewrote our equation. And now we have to use what we know. So we were told that f of 1 equals 10, and f prime of x is bigger than 2 for every x. So in particular, f prime of c, because it's f prime of x for some x, we don't care what, every derivative is bigger than 2, so in particular, f prime of c is going to be bigger than or equal to 2. So we have f of 1 is 10, and then we have 3 times something which is bigger than 2. So we're going to get an inequality for f of 4. Right, f of 4 is going to be equal to first term 10, then the f prime of c is bigger than or equal to 2. So we get 10 plus 3 times 2, we get 10 plus 6, we get 16. Okay, so f of 4 is bigger than or equal to 16. So this is the smallest that f of 4 could possibly be. And actually, it can be that small, for instance, if we were to pick, we could pick a function which is just a linear function or a constant, and you could realize the 16. Okay, so this is the smallest possible. Okay, so notice, again, it has the same the same giveaways, right? That it's continuous on the closed interval, it's differentiable in the open interval. We know something about the derivative for every value of x. Okay, maybe it's a good idea to use the mean value theorem. Okay, so we did that. And here's one more example. Let's use the mean value theorem to prove that the absolute value of sine A minus sine B is less than or equal to the absolute value of A minus B for all A and all B. Okay, so it seems like, we have a function sine x, but it seems like we weren't told anything about the derivative. But we already know a bit about the derivative of sine x, right? The derivative of sine x is cosine x. And we know that cosine x is always between -1 and 1. So actually, we know something about the derivative of sine for every x. It's always between -1 and 1. Okay, so let's try to use that. So it's differentiable, it's continuous. Trig functions are very nice, beautiful functions, in particular, continuous and differentiable. So we can naively jump in and use the mean value theorem on an interval AB. So by the mean value theorem, we just write the statement. There is C in the middle. We don't know what C is, but it doesn't matter. So that f of B minus f of A equals f prime of C times B minus A. Okay, but this is just naively, writing the definition. What does that mean for the theorem? What does that mean for our function? So our function is sine x. So I'm going to get sine of B minus sine of A. And the derivative is cosine x. So I'm going to get cosine of C times B minus A. So just writing the same thing out, but with our particular function sine x, we get this equation. And now we had something about absolute values. So let's take absolute values at both sides, which is completely fair game as long as we do the same thing to both sides. So if we do that, we get the absolute value of sine B minus sine A is equal to absolute value of cosine C, absolute value of B minus A. And now we want to use the information we know. So we said that cosine C is always between -1 and 1. So the absolute value of cosine C is always less than or equal to 1. Okay, so the absolute value of cosine C is less than or equal to 1. So now if we use that fact, we're going to get absolute value of sine B minus sine A is less than or equal to 1 times the absolute value of B minus A. Okay, which is exactly what we wanted. Okay, here I swapped around the A's and the B's, but that doesn't matter because we have an absolute value. So if I swap the sign of the inside, it doesn't matter because the absolute value gets rid of the sign. Okay, so using that fact that the absolute value of cosine is less than or equal to 1, we managed to prove the exact inequality we wanted. Okay, so keep in mind that the fundamentals from this were Rolle's theorem, but that's more of a stepping stone to get towards the mean value theorem. So mean value theorem said that if our function is continuous on the closed interval, differentiable in the open interval, then at some point C in the middle, it doesn't tell us where, but at some point C in the middle, f prime of C is f of B minus f of A, f of B minus A. There are multiple ways to interpret that using lines or using rates of change in physical problems. And then this was really useful if we know something about the derivative for every value of x. For instance, if we have an inequality or if we know the derivative is 0, because the mean value theorem doesn't tell us what C is. Okay, thanks everyone. See you next time. Take care.